There is a question that quietly haunts physics, philosophy, and technology alike. What if everything we experience, space, time, matter, even thought, is the output of a vast computation? It sounds like science fiction, yet some of the world's most serious scientists treat it as a legitimate possibility. In 2003, Oxford philosopher Nick Bostrom proposed the simulation argument, Philosophical Quarterly, claiming that at least one of three statements must be true. Civilizations never reach a level capable of running universe-scale simulations. They reach it but choose not to, or we are almost certainly living inside one already. The logic is brutally simple. If any advanced civilization creates billions of conscious simulations, then statistically, almost every conscious being must live in one. The idea isn't mystical, it's mathematical. The universe behaves like information. At the deepest level, physics is written in bits, not atoms, discrete packets of data that obey rules perfectly described by equations. From Einstein's field tensors to quantum probabilities, everything can be reduced to relationships between numbers, and if something can be expressed entirely as information, it can, in theory, be computed. Modern cosmology and computer science are beginning to overlap. Researchers at MIT and CERN publish on computational cosmology, the view that the universe could operate like a self-updating system, processing roughly 10 circumflex, 120 operations since the Big Bang. Seth Lloyd's work, Phys. Rev. Let. 2019, describes the cosmos as the ultimate quantum computer, where every particle interaction performs a logical operation, storing the history of reality in its quantum states. But beneath the equations lies something deeply human, the unease that perhaps reality is not continuous, but rendered. The cosmic background noise, quantum indeterminacy, even the finite speed of light could be hints of a processing limit, the frame rate of existence itself. Every observation we make might be a pixel refreshed when measured, not before. Yet if we are inside such a system, who or what built it? The idea forces a confrontation between science and theology, between silicon logic and metaphysical purpose. Are we the first generation intelligent enough to detect the code that sustains us? Or just one more simulation asking questions its designers expected? Physicists warn against jumping to conclusions. The simulation hypothesis isn't a claim of belief, it's a framework for testing. Quantum computing, Planck-scale physics, and cosmic background data are slowly giving us tools to look for the seams in the universe's fabric. For the first time in history, the question, are we real, can be asked with equations instead of philosophy. And that question, whispered across disciplines, may become the one that rewrites our understanding of existence itself. If the simulation hypothesis has a foundation, it's built from numbers. Every law of nature, from gravity to quantum tunneling, can be written as mathematics. And that isn't just convenience. Many physicists believe the universe is mathematics, a self-consistent structure of relationships that exist independently of any physical medium. This idea, championed by Max Tegmark of MIT in his mathematical universe hypothesis, suggests that reality doesn't merely follow math, it is math. Electrons orbit because of equations. Galaxies form because differential tensors predict they must. In this view, physical reality is a subset of mathematical reality, an equation that became self-aware. If this is true, then the physical universe and a computer simulation are separated only by implementation. Both consist of logic evolving in time according to precise rules. Change the substrate silicon, space-time, or something else entirely, and the computation persists. Reality, then, is not a thing, it's a process. Evidence for this perspective hides in plain sight. When we measure fundamental constants, Planck's constant, the fine structure constant, the speed of light, they appear unitless, dimensionless, almost suspiciously precise. These constants define the resolution of the universe's operating system. Adjust any one of them by even a fraction and atoms wouldn't hold together. Yet, they remain fixed, as if locked parameters in a cosmic program. In 2022, researchers at CERN studying high-energy collisions noticed symmetry patterns that echoed computational optimization physics, behaving as though it were minimizing energy functions, just as machine learning models do when training. The mathematics of renormalization, the process that keeps infinite quantities from breaking equations, mirrors the way simulations conserve precision under limited resources. The cosmos, it seems, runs on perfect efficiency. Even the structure of space hints at an underlying code. Theoretical work on quantum gravity describes spacetime as discrete rather than continuous, a network of interlocking mathematical nodes called spin networks that resemble the logic gates of a computer. Each interaction updates the state of the network, step by step, just as code executes line by line. If the universe is truly mathematical, it also explains why it's intelligible. Our brains, products of evolution, shouldn't necessarily comprehend the workings of galaxies and particles, yet mathematics, an invention of human abstraction, fits the universe with uncanny precision. As physicist Eugene Wigner wrote, "The unreasonable effectiveness of mathematics in the natural sciences might itself be the clue we've ignored." Perhaps we are not discovering the universe's equations, we are remembering them. In a mathematical universe, consciousness is not an anomaly. It's the equation solving itself, aware that it's running. And if existence is numbers unfolding in time, then asking whether we are in a simulation might be redundant. We already are, because the laws that define everything are indistinguishable from code written in a language called physics. If the universe is built on information, then quantum mechanics is where that information hides. At the smaller scale of reality, the Planck length, about 1.6 times 10 to the power of negative 35 meters space itself, may no longer be continuous, but pixelated. Beneath the smooth curves of spacetime lies a lattice of discrete values, the universe's binary foundation. In the 1980 seconds, physicist John Archibald Wheeler coined a phrase that still shapes theoretical physics: it from bit. He proposed that every physical entity, it, ultimately derives from a binary choice, bit, the yes or no questions nature answers whenever we make a measurement. Every photon, every particle, every field can be described as information stored and updated by interactions. Reality, then, is not made of stuff, but of decisions. Quantum theory supports this interpretation. Particles do not have definite states until they are measured. They exist in superposition, a set of probabilities representing all possible outcomes. When observation occurs, the wave function collapses and one result is realized. This act of measurement is not just passive, it's computational. The universe renders a value when required, much like a processor updating a pixel only when it appears on screen. Recent work by physicist Vlatko Vedral and Anton Zeilinger's experiments in quantum entanglement reinforce this view. When two entangled particles remain correlated across vast distances, the information describing them stays perfectly synchronized, as though both are entries in the same global database, updated instantly, regardless of separation. Einstein called it spooky action at a distance. Today, quantum information theory calls it shared data across a non-local system. The Planck scale may mark the smallest bit size the universe can process. Below that, classical concepts like space and time dissolve into noise. Simulations built on lattice quantum chromodynamics already mimic this structure, a finite grid where matter fields are computed cell by cell. The resemblance to reality is uncanny, almost as if physics discovered the same constraints any coder would face in building a perfect world from scratch. Even energy itself behaves like a storage system. Quantum fields can be thought of as repositories of information density. When particles interact, they exchange bits of that data. Conservation laws, momentum, charge, energy become rules for keeping the cosmic database consistent. Violating them would crash the system. This perspective doesn't trivialize reality. It clarifies it. A star, a human, a galaxy, all are emergent expressions of underlying information, processed by natural laws with precision beyond any computer we've built. If the universe is a quantum program, then existence is not random, it's logical. Each particle interaction is an instruction executed flawlessly since the dawn of time. And if those instructions ever stop, the universe stops too. Until then, we are living data matter that has learned to ask how its own code works. At the heart of quantum mechanics lies a mystery that has never been fully resolved. Why does observation change reality? When a particle is unmeasured, it behaves like a wave, a blur of probabilities spread through space. Yet the instant it is observed, it chooses a single outcome, as though awareness itself triggers the collapse. This phenomenon, known as the observer effect, is not philosophical speculation. It is experimental fact, confirmed countless times through the famous double-slit experiment. In that experiment, electrons fired through two slits produce an interference pattern proof of wave behavior until detectors are added to see which slit they pass through. The moment we measure them, the pattern vanishes. Each electron behaves like a localized particle. The universe seems to decide based on whether anyone is watching. What is the observer in this context? A conscious mind? A physical interaction? Or an active information exchange? The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, treats observation as any interaction that extracts information. But newer interpretations, like quantum information theory, go further. Observation is computation. Measurement doesn't merely reveal data, it creates it. The universe updates its state through informational transactions, just as a simulation refreshes its frame when queried. In recent years, experiments by Eugene Polzik's group at the Niels Bohr Institute and Ephraim Steinberg's lab in Toronto have shown that measurement can steer quantum systems without destroying coherence, as if the act of knowing rewires the probability landscape. Physicists now model these processes with quantum Bayesianism, cubism, where the observer's knowledge, literally their information, reshapes the system's description. This brings an uncomfortable symmetry. If consciousness is defined as the capacity to process and update information, then the universe's own behavior looks eerily similar. Observation may be the dialogue between code and cognition, the system rendering outputs in response to informational queries. Philosophers like David Chalmers have suggested that if simulated realities can host conscious beings indistinguishable from biological ones, then consciousness itself must be substrate, independent, a pattern, not a product. In that case, minds are algorithms running on matter, and matter is information rendered from mathematics. Observation becomes feedback between nested levels of computation, us observing the universe, and the universe observing itself through us. The implication is profound. Consciousness is not outside the system trying to understand it. It's a process within the system that completes its equations. Reality needs observers, because observation is part of how the program runs. Perhaps that's why the cosmos is knowable at all. Awareness isn't an accident, it's a feature of the code, the mechanism through which existence becomes self-referential. And if that's true, then every act of seeing is also an act of creation, each observation collapsing probability into reality, one measured bit at a time. Every digital simulation, no matter how realistic, has a resolution as small as possible unit of space and time. Zoom in far enough, and even the most detailed rendering reveals its pixels. Physicists suspect our universe might do the same. At the deepest scale of reality lies the Planck length, about 1.616 times 10 to the power of -35 meters. Below this threshold, space itself loses meaning. There is no smaller distance, no measurable geometry. This is not a limitation of our instruments, it's a boundary written into nature's code. The same goes for time. The Planck time, roughly 5.39 times 10 to the power of -44 seconds, may represent the smallest possible tick on the universe's clock. Together, these constants define the smallest possible frame in the cosmic rendering engine. In quantum gravity theories, like loop quantum gravity, space isn't a continuous fabric, but a vast lattice of discrete loops, tiny quanta of area and volume that combine to form everything we perceive as smooth. Space-time, in this view, is granular. The universe doesn't compute infinity, it calculates in finite bits. This pixelated model is more than metaphor. In 2015, researchers at Fermilab began the holometer experiment, designed to test whether space-time jitter tiny random fluctuations might betray a fundamental resolution limit. The idea was radical. If reality has pixels, then even empty space should vibrate slightly as the cosmic screen refreshes. While no definitive jitter has been found yet, the experiment set upper limits that continue to refine how finely the universe can render detail. Other physicists are approaching the question through the holographic principle, which suggests that the universe's information content is not stored in 3 dimensions, but on 2-dimensional surfaces, the cosmic equivalent of compressed data. Every cubic meter of space could hold no more than about 10 to the power of 69 bits of information. Beyond that, physics breaks down. This limit, known as the Bekenstein bound, acts like a universal bitrate cap, constraining how much information can exist in any region of space. Even black holes follow this rule. Their entropy, the measure of information they contain, is proportional not to their volume, but to their surface area. When a star collapses into a black hole, its information isn't destroyed, it's encoded on the event horizon in Planck-sized units. Space behaves as if it's a screen recording every detail that ever crossed it. If this is true, then our entire universe might be a projection, a high-resolution rendering on a cosmic boundary, refreshed 1 Planck tick at a time. That would mean what we experience as continuous motion is an illusion born from rapid updates, like frames in a film. The speed of light could be the frame rate limit, roughly 3,000,000 kilometers per second, the fastest anything can move through the grid before the simulation blurs. This framework aligns with the digital physics school of thought pioneered by Edward Fredkin and Konrad Zuse, who argued that the universe operates like a cellular automaton, a self-evolving code updating in discrete steps. What we call laws of nature are the algorithmic rules that determine how each cell interacts with its neighbors. If every Planck scale interaction is one computational operation, then the universe is performing about 10 to the power of 43 updates per second per Planck volume. That's not metaphor, it's math. Reality may not be infinite, it may simply be very, very high resolution. And if space-time itself is quantized, then the difference between physics and programming becomes one of perspective. Both are systems bound by finite precision, updating frame by frame. Every digital system, no matter how vast, requires error correction. Without it, even the smallest bit flip caused by noise or interference would cause information to degrade. Your phone uses it, supercomputers use it, and, astonishingly, physics may use it too. In 2014, theoretical physicist Juan Maldacena and quantum information scientist Leonard Susskind published a paper that stunned both communities. They suggested that space-time geometry, the very shape of the universe, might be built from quantum entanglement and maintained by error-correcting codes. The structure that keeps black holes stable and prevents information from being lost could be the same mathematical principle that keeps digital data intact. This idea grew from the puzzle known as the black hole information paradox. When something falls into a black hole, classical physics says its information disappears forever. But quantum theory forbids information loss. It violates the most fundamental rule of computation, reversibility. If the universe truly runs like a system that can be simulated, every interaction must be perfectly traceable, even if scrambled beyond recognition. The proposed solution was stunning. Black holes don't destroy data, they encode it. Their event horizons act as quantum error, correcting surfaces that store and preserve information in highly redundant ways. When Hawking radiation emits particles, it slowly releases that encoded data back into the universe. In other words, reality fixes its own glitches. To test these concepts, physicists began mapping parallels between quantum field theory and computer science. In 2017, researchers at the Perimeter Institute and MIT discovered that space-time equations could be replicated using a type of quantum error-correcting code known as a tensor network. Each node represents a quantum bit, and the connections between them preserve overall structure even when individual bits are lost. The result? A self-healing universe mathematically indistinguishable from a massive redundant database. Even the holographic principle, which suggests that all of three-dimensional reality is encoded on a two-dimensional surface, relies on this property. Every bit of spatial information is redundantly stored across countless Planck-scale pixels, ensuring the universe's internal consistency. It's as if the cosmos is programmed to never lose data, no matter how chaotic its processes become. This insight has transformed theoretical physics. The same mathematics used in quantum computing stabilizer codes, entanglement networks, and logical qubits now describe how gravity might emerge from information itself. The equations of general relativity could be byproducts of the universe, maintaining coherence, frame by frame, like a perfect checksum running beneath reality's surface. If this sounds abstract, consider its implication. Every law of physics from thermodynamics to electromagnetism might exist because the universe is designed to preserve information integrity. Matter, energy, and geometry are the visible byproducts of a cosmic operating system, ensuring its code never corrupts. In essence, what we call reality could be a continuous act of error correction, an endless recalibration that prevents existence from unraveling into noise. And if this holds true, it means something extraordinary. Even black holes, the universe's most destructive forces, are not erasers. They are archivists, guardians of information that will never be lost. Imagine that everything you see, space, time, matter, light, isn't truly three-dimensional, but a projection, a perfect illusion generated by information inscribed on a distant surface surrounding us. This is not science fiction. It's one of the most serious ideas in modern theoretical physics, the holographic principle. The story began with Jacob Bekenstein and Stephen Hawking, who discovered something strange about black holes. Their entropy, the measure of how much information they contain, did not scale with their volume, but with their surface area. A black hole's information capacity depends on how much of the event horizon you can cover in Planck-sized tiles. The deeper you fall in, the more you realize the universe stores data like a hologram on surfaces, not within volumes. In 1997, physicist Juan Maldacena connected this idea to the entire universe through the adds divided by CFT correspondence, a mathematical model linking two very different worlds. On one side, a universe with gravity, depth, and space-time curvature. On the other, a flat, two-dimensional field of quantum particles interacting without gravity. And yet, every event in the 3D world perfectly mirrors the information encoded on the 2D surface. Reality, in this framework, behaves like a hologram, where the illusion of depth arises from data patterns written on a lower dimensional boundary. The implications are staggering. If this principle applies beyond black holes, if it governs all spacetime, then our entire universe could be a projection of information stored on a cosmic horizon tens of billions of light years away. What we experience as physical distance might simply be the unfolding of mathematical relationships between encoded bits. Recent research has strengthened this possibility. Studies by Eric Verlinde and others have proposed that even gravity itself might not be a fundamental force, but an emergent phenomenon, a byproduct of information distribution within a holographic system. According to this view, the curvature of spacetime isn't caused by mass and energy directly, but by how information is arranged and processed. Gravity becomes an illusion born from entropy gradients, heat, and data shaping motion through geometry. Observationally, this holographic model can even predict the tiny quantum fluctuations that gave rise to galaxies. In 2017, researchers analyzing the cosmic microwave background found subtle statistical patterns that match predictions from holographic cosmology. If verified, it would mean the entire Big Bang could be understood as a kind of informational rendering where space and time emerged from quantum entanglement across a vast cosmic surface. This doesn't mean we live inside a digital projection like a computer screen. It means that the mathematics governing reality might work that way. The universe behaves as if it's compressing and projecting data efficiently, following the same logic that drives holograms or error-correcting codes. And perhaps that's the deeper truth behind the simulation hypothesis, not that someone is running the universe on a computer, but that the universe is computation structured in ways that conserve and project information flawlessly. If reality is a hologram, then depth is an illusion of data. Every moment, every star, every human thought could be part of a grand rendering written not in pixels, but in Planck-scale bits of encoded geometry on the boundary of space. If the universe is information, then something must connect it. Something that links every atom, every photon, every event in space-time into a coherent whole. That something may be quantum entanglement, the invisible web Einstein once dismissed as spooky action at a distance. Entanglement is the phenomenon where two or more particles become correlated so perfectly that measuring one instantly defines the other, no matter how far apart they are. Break them apart by light years, and they still behave as one system. It's not telepathy or hidden signals, it's a fundamental feature of how reality stores information. In quantum mechanics, entanglement is not the exception, it's the rule. Over the last decade, physicists have begun to realize that entanglement may be far more than a curiosity. It may be the operating system of the universe itself. Theorists like Mark van Ramsdonk and Brian Swingle have shown mathematically that the structure of space-time might actually emerge from networks of entangled particles. In their models, connections of quantum information literally weave the geometry of the universe. Remove enough entanglement, and space-time itself begins to unravel. This idea finds its most striking evidence in the ads divided by CFT correspondence, the holographic theory first proposed by Juan Maldacena. In this framework, entanglement between quantum bits on a two-dimensional boundary constructs the three-dimensional bulk of space-time. The more entangled the system, the smoother and more connected space-time becomes. If the entanglement weakens, wormholes stretch and geometry disintegrates. In essence, gravity and distance could just be side effects of quantum information being shared. Experimental physics is now beginning to probe this idea directly. In 2022, scientists at Fermilab and Google Quantum AI simulated a miniature version of a holographic wormhole using a quantum computer. It wasn't a tunnel through real space, but it was a mathematical analog. By manipulating entangled qubits, they reproduced the same information flow that general relativity predicts for wormhole teleportation. In other words, the fabric of space can be emulated through entanglement proof of concept that spacetime itself might be computation in motion. This brings us to an even larger realization. The universe could operate like a quantum internet, a vast, self-sustaining network where every particle is a node, every interaction a data exchange. Information doesn't just travel through space, it defines it. And entanglement ensures that this information remains consistent everywhere, even across billions of light years. If that sounds abstract, consider this. Quantum entanglement already underlies our most advanced technologies. Quantum teleportation, quantum encryption, and the emerging global quantum web all rely on the same physics that may knit the cosmos together. The same principle that keeps data secure across lab experiments could be the same rule that keeps reality coherent on a cosmic scale. It's possible that consciousness itself, the ability to experience, perceive, and interact, is simply a localized interface within this entangled network. We are not outside observers of the simulation. We are participants, entangled nodes, processing and transmitting information through thought, perception, and energy. The universe might not be made of things at all. It might be made of relationships. Every atom, every wave, every law of physics could emerge from a deeper architecture of information exchange. And in that sense, entanglement is not just a feature of the quantum world, it is the internet of existence itself. The invisible connection that keeps the simulation running, one quantum update at a time. If the universe truly behaves like a computation, then somewhere in the code there should be imperfections, glitches, rounding errors, or seams where the resolution breaks. Physicists call them anomalies. And though most turn out to be noise or measurement error, a few have forced the scientific community to look twice at the possibility that our cosmos has limits built into its architecture. One line of investigation comes from high-energy cosmic rays. According to special relativity, ultra-energetic particles should obey predictable behavior as they travel through space. Yet several detectors, including the Pierre Auger Observatory in Argentina, have recorded particles that appear to violate expected energy ceilings. A minority of researchers interpret these outliers as signs that space-time itself may have a maximum refresh rate, like pixels in a simulation that can't process faster than a set frame rate. At the Fermi Gamma Ray Space Telescope, scientists searched for dispersion-tiny delays between high and low-energy photons arriving from distant gamma-ray bursts. If reality had a discrete, quantized structure, the highest energy photons would slow down slightly, revealing a kind of cosmic lag. So far, the data remain inconclusive. No clear lag, but just enough uncertainty to keep the question alive. Another clue hides in the fine structure constant, the dimensionless number that determines how strongly light and matter interact. Across billions of years and thousands of observed galaxies, this constant has stayed almost perfectly the same, but not exactly. A few measurements suggest it drifts by a few parts per million. That might be random variation or the slow recalibration of an underlying computational grid. Quantum experiments on Earth reveal similar curiosities. In superconducting circuits, researchers observe persistent quantum correlations that shouldn't survive thermal noise. In entanglement studies, particles behave as if they know they're being measured, maintaining coherence longer than classical physics allows. To most physicists, this reflects hidden variables or experimental imperfections. Yet to others, it hints that observation itself, our awareness, may be built into the program's rules. Even the cosmic microwave background, the oldest light in the universe, holds potential hints. Subtle temperature alignments, known as the axis of evil, refuse to fit standard cosmological models. The pattern could be coincidence, or the visible fingerprints of the simulation's boundary conditions, the edges of rendered space. Still, caution rules the field. Extraordinary claims require extraordinary evidence, and so far, every anomaly has alternative explanations within known physics. But the persistence of near coincidences, the sense that our equations are almost too elegant, our constants too fine-tuned, continues to fuel curiosity. Some experiments now go further, like Silas Bean's lattice universe proposal. If space is discretized, then extremely high-energy cosmic rays should reveal a telltale angular pattern mimicking the grid of their simulated spacetime. Future detectors may finally be able to test that prediction. For now, we remain inside the code, searching for cracks in the display. Every time we probe deeper into quantum noise, cosmic radiation, or the constants of nature, the simulation, if it exists, hides its seams a little better. Each unanswered question feels less like a flaw and more like design, an intentional blur at the edge of resolution, where physics fades into information and mystery begins. If the universe is a simulation, the final mystery isn't how it runs, it's why. Behind every system lies intent, a purpose, a function, a reason it was built. But when the system in question is reality itself, that question becomes almost unbearable. The idea isn't new. Philosophers from Descartes to Nick Bostrom have asked whether existence might be a grand illusion. Bostrom's argument, now famous, is statistical. If civilizations ever develop the ability to simulate conscious beings, and if they choose to do so many times, then simulated worlds would vastly outnumber real ones. Logically, it becomes more probable that we are in one of the simulations than in the single, original universe. But motive is harder to compute. Some theorists suggest that a simulated cosmos could be an experiment, a vast physics engine designed by post-human descendants to study the laws of nature or the evolution of intelligent life. In that view, our reality is a controlled environment, a lab where variables like gravity, entropy, and biology are allowed to play out. Others imagine it as an archive. Advanced beings might run ancestral simulations to preserve the memory of where they came from, recreating lost histories, civilizations, or even entire epochs. In that scenario, we are not test subjects, but echoes, conscious records keeping ancient knowledge alive through repetition. A more speculative idea ties directly to quantum mechanics. Perhaps the act of observation that defines our universe, the collapse of wave functions into definite outcomes, is part of the simulation's efficiency. Reality renders only when observed, conserving computational power. This would explain why, at its deepest levels, the universe behaves probabilistically. The code is optimized. And then there's the possibility that there is no creator in the way we imagine. Perhaps simulations emerge naturally, like self-replicating patterns in mathematics. Once a universe capable of computation arises, it spawns others nested realities, each simulating the next, an infinite cascade of creation through information. In such a framework, purpose is replaced by process. The universe doesn't need a reason to exist. It exists because information, by its nature, seeks to organize itself. Yet the human mind resists that indifference. We are built to ask why, to find meaning in patterns. Maybe that's the true design feature, not in the physics, but in us. Our curiosity, our need to explore, might be the simulation's goal, a mechanism ensuring that the system keeps evolving, learning about itself through its conscious components. Whether we were programmed by ancient intelligence, generated by emergent physics, or simply exist as a natural computation, the conclusion is the same. Meaning is not handed down from outside the code. It's generated within it by conscious beings capable of reflection. If reality is simulated, then understanding it is participation. Each discovery, each equation, each observation is a line of code writing itself. The universe may not have been created for us, but it is, in a profound sense, through us that it becomes self-aware. So perhaps the question isn't, why was it created? But why are we the ones inside it asking? Because maybe that the act of wondering is the reason the simulation exists at all.